Hello and welcome to the webinar. So today we will set up your first HPC cluster on AWS. My name is Francesco Ruffino and I am HPC specialist. I'm a solution architect in AWS. So this is the agenda for the webinar today. The tool that we are going to use to set up your first HPC cluster is AWS ParallelCluster. So in the beginning, I will explain to you what is ParallelCluster, what is the architecture, how you can install it, how you can configure, and then we will run your first MPI job. And then we will run through some more advanced configuration. And then finally, we will have some interactive question and answer. So let's start from the first point. What is AWS ParallelCluster? ParallelCluster is an AWS supported open source tool, and the goal of ParallelCluster is to make it easier for you to manage and deploy an HPC cluster on AWS. ParallelCluster is kind of an evolution of CFN Cluster. CFN Cluster was an open source project run by an AWS solution architect, but last year we have decided to evolve this tool in a supported project, and we have also added some important functionality, and so we have decided then to rebrand it as ParallelCluster. So since it is an open source project, here you can find the GitHub link where you can download the source code and also read the manual. We have also published some tutorial, so you will find a lot of information starting from this link. So what are the features of ParallelCluster? As I said before, the goal of the tool is to make it easier to deploy and manage an HPC cluster. So the idea is that you will continue to use the job scheduler you are using on-prem, so like SandGrid Engine, Torque, and Slurm, but ParallelCluster will automatically deploy this job scheduler for you on AWS, and plus will manage the elasticity of the cloud. So that means that you will just need to submit your job in the traditional way, so using the commands you are familiar with, and then ParallelCluster will take care of starting and stopping the computing instances for you based on the user needs. At the moment, as I said, we do support SandGrid Engine, Torque, and Slurm, but we are planning to add many more job scheduler in the future. And plus, we are also ParallelCluster can also support AWS Batch, that is the AWS job scheduler. But this is not the only thing ParallelCluster can do for you. ParallelCluster will also, for example, deploy a shared file system between the master node and the computing node, and many other features that will really simplify the day-by-day management of your HPC cluster. This is the high-level architecture of the product. The idea here is to basically decouple the administrator view from the user view. So we want, as I said before, the user to be able to interact with ParallelCluster in like traditional on-prem cluster. But at the same time, we also want to give to the administrator the possibility to configure and optimize the deployment on AWS. For this reason, the ParallelCluster architecture is composed of three different elements. We have the ParallelCluster client, the ParallelCluster master, and the ParallelCluster computing nodes. So the ParallelCluster client can be deployed, is the tool that will be used, is a command line tool that will be used by the administrator. And you can deploy it on-prem or on AWS. What the client will do for you, according to the administrator configuration, it will deploy a CloudFormation template, and the CloudFormation template will deploy the ParallelCluster master. Then the user can connect via SSH to the ParallelCluster master, and as I said before, they will just submit their jobs using the qsub command, for example. What ParallelCluster will do behind the scene is that it will continuously check the user request, and this will trigger an autoscaling group. And the autoscaling group will start for you the computing nodes based on the needs of the users. So if your user need to run a jobs on 10 computing nodes, the atom scaling group will start 10 nodes, 10 EC2 instances, will execute the job, and when the job is done, will also terminate automatically the instances. So we have seen the high-level architecture. Now let's have a look on how to deploy it. The first step is to install the ParallelCluster client. The client, the command line, is really the most important configuration point, let's say, for ParallelCluster. So we'll see how to deploy the ParallelCluster client, how to configure it, and then what are the commands that you can use in order to deploy your first cluster. So let's talk about the installation. What are the requirements for the ParallelCluster client? So first of all, you can deploy the ParallelCluster client on-prem or on AWS. It's really up to you. The requirements are, from the operating system point of view, ParallelCluster can support Linux and macOS, while Windows is experimental at the moment. Anyway, you will see later that I'm currently using Windows for my own ParallelCluster client installation, and the trick here is what I'm using, let's say, is the Linux subsystem, the Ubuntu Linux subsystem that is available on Windows 10. So this basically it's a kind of Linux interface running on top of Windows, and you can easily deploy ParallelCluster on top of it. And this is what we will do in a minute. Then on top of that, you need Python. You need also to install the AWS command line. You need PIP to manage the installation, and it's not really it's not a must, but it's recommended also to use virtualenv in order to manage the different Python libraries. So these are the installation commands. This is what basically I'm going on, what I have used, what we are going to use in the next step. I have just done a cut and paste for you, so you can later on you can just repeat the step that we have done, that we will do during this webinar. Probably you already done some of those, like the installation of the command line and so on. As you can see, the AWS ParallelCluster installation, it's very easy. It's just the pip install AWS ParallelCluster command. Okay, that's been said. Let's go live and let's install the ParallelCluster client. Okay, there we go. So let me start my virtualenv. Perfect, this is done. Now enter my virtualenv, and from here I can start the installation. There we go. Install pip install AWS ParallelCluster. Okay, there we go. I have already pre-installed many libraries, so this is really fast. Okay, fantastic. We have installed the ParallelCluster command line. Now let's have a look at the commands that we can use. We have the create command, obviously, that create the cluster, but we also have the update command. So if you, for any reason, you need to change the configuration of the cluster, you can edit the configuration file, and then with the update command, you will refresh the deployment that is running on AWS. You can then start or stop the compute fleet. You can delete the entire cluster if you want. You can check the status of the cluster. And you can also have a list of the cluster, because probably you will have several different clusters deployed on AWS at any given time. And the reason is because maybe you will have different user needs, and you may want to map these different user needs to different clusters. And as I said before, cluster basically is just a CloudFormation stack. So the list command will give you a list of all the stack that are associated with AWS ParallelCluster. Then you can have the list of the instances, and you can also interestingly connect to the master instance using the SSH command. So you don't even have to give to your user the master IP address if you don't want to. Then we have a command to create a new AMI if you want to customize the AMI that we are using. And we have also a wizard that will help you to configure ParallelCluster. Okay, so we have installed it. Now let's jump to the configuration. Before we start, there are some information that you have to collect. First of all, the SSH keys that you want to use to connect to your master node. Then obviously you have to select the region where you want to run it and the VPC that you want to use. Then you have also to select the subnet where your EC2 instances will be deployed. And then you have also to select the instance type for the master node and another instance type for the compute node. You can use the same one, but usually the compute nodes are the one that will actually run your job. So the computing nodes are the instances that will require more CPU power or more memory and so on. While the master node will just be kind of bastionos that will collect all the command and then submit those to the computing nodes. So most of the cases you will not really need a very high-end instance type for your master node. Then, as I said before, there is a wizard that can help you to configure, to have a first configuration, and this is the ParallelCluster configure command. So let's see how it works. Okay, here we go. So let's run ParallelCluster configure. We can accept the default here. As you have noticed, I have not entered my access key and my secret access key. The reason is if you specify them, ParallelCluster will save the credential in the ParallelCluster config file. I don't think this is a good idea. Let's say I think it's probably easier and safer to keep your credential in your environment, so that if you want, you can easily share the config file with your colleagues without worrying about removing the credential from the configuration file. Then we have to select the region, as I said before. So in my example, I will run in the Ireland region, a West 1. It also show me the SSH key that are available. So I will select one of those. And then it will list all the VPC that I have on my account. So we can select one of those. And then it will give you the list of the subnet. So you can also select subnet for your EC2 instances. Okay, there we go. We are done. So this is all basically for the initial configuration. Now we can, let's say, dive deeper and then a more detailed configuration. As I said before, the next thing is to configure the instance type, to select the instance type for your workload. So in this table here, I have summarized some. As you know, we have a huge variety of EC2 instances that you can use them for several different goals. So here I have summarized some of the technical details of the EC2 instances that we are using more often for HPC workload. These are the M5, R5, C5, and Z1D, P3, G3, and F1 instance type. So in this table, the reason why I'm sharing this table with you is because I think it's then easier to select the best instance type for your needs. Here you can see the CPU frequency for each instance type, the max memory that is available, and also the number of vCPU and cores. Please keep in mind that all these instances are running on hyper-threaded cores. So a vCPU basically is an hyper-thread core. So that means that if you want to know the number of the physical cores, you have to halve the number of the CPUs, of the virtual CPUs. So then I have also inserted here the number of the memory per core or the memory per vCPU. This can be useful because, as you know, some applications require a minimum amount of memory per core. And then some of these instances, the one equipped with the small d, like the M5D, this one have also a local NVMe disk that is very fast disk, and this is very useful if you have to run an IO intensive type of application. And then finally, the network bandwidth, the network adapter, and the accelerated computing device. For example, the P3, as you know, runs on NVIDIA Volta V100. You can run up to 8 NVIDIA Volta on one single EC2 instance. The G3 runs on the NVIDIA Tesla M60, while the F1 is our FPGA instance. Then it can go up to 8 Xilinx FPGAs on one single node. So I have also highlighted 2 new instances that we have announced at reInvent November 2018. These are the C5N and the P3DN. These are really interesting for the HPC use case. The C5N is a kind of refresh in our C5 family, and it has more memory per core. The CPU is the same as the C5, but this one is equipped with more memory per core, and we have also increased the memory bandwidth. But most importantly, these new instances are running on our new network that can go up to 100 gigabit per second. And this is true both for the C5 and the P3DN. And then most importantly, these can also run on EFA. EFA is a new network adapter that we have just announced a couple of days ago, and let me jump into it. So, what is EFA? EFA is a new network adapter that is a kind of evolution of the ENA, so the Elastic Network Adapter. EFA can still handle the IP traffic, but it also supports an important access model that is commonly called OS bypass. So the idea is that using EFA, your application don't need to interact with the kernel when have to connect to the network. So basically, we can use MPI and libfabric in order to bypass the Linux kernel and interact directly with the EFA device. This will radically reduce the overhead and allows the HPC application to run more efficiently. This is particularly true when you are going to run tightly coupled type of application, because EFA can reduce the MPI latency, the one-way MPI latency to 15.5 microseconds. So your tightly coupled type of application, while running on the new network with EFA, will experiment on a relevant improvement in terms of performance. And here is the link of a blog post, a Jeff Barr blog post, where you will find more information regarding EFA. So this will hopefully help you to decide how you want to configure parallel cluster. So here, for example, in my example, I've selected the C5 for the compute instances and the M5 for the master instances. You can also select the initial and max queue size. This is very important. So this is basically the number of computing nodes that you want to run. The initial queue size is the number of computing nodes that would run after the deployment of parallel cluster. So if I set it to 0, that means that just after the deployment, you will have 0 computing nodes. But then obviously when the user starts to submit, parallel cluster will start the computing nodes for you. And the max queue size, as you might expect, this is the maximum number of computing nodes. So in my example, I will never have more than 10 computing nodes running. This is obviously, this can be customized obviously, so it's up to you to decide. And this will create a cap of the maximum number that you will run. Please remember that you can freely configure this number as you wish, but then you have also to double check if this is compatible with your limits. As you know, every instance has different limits, and you can raise the limits if you want, but you have to use the AWS console if you want to increase the limits for a specific instance type. The maintain initial size parameter, if it is, in my example, is set to false. If it is set to true, it means that no matter how many jobs you have in the queue, parallel cluster will always maintain a certain amount of computing nodes. So if, for example, if you set the initial queue size to 2 and the maintain initial size to true, you will always have 2 computing nodes up and running, even if there are no jobs in your cluster. Then you can select the placement group. As you know, for tightly coupled type of application, it's very important to run on a cluster placement group. And if I selected this as dynamic, that means that for every job I submit, parallel cluster will create automatically a cluster placement group for me. And then you can also configure your scaling setting. For example, in this case, I have set the scale down idle time to 1. That means that if there is no job running on a compute node, after 1 minute, the node will be automatically terminated. If you want the node to be more persistent, you can increase this value to, I don't know, 5 minutes, 10 minutes, so it's up to you. And then, as you can see, you can also specify the operating system. The default operating system is Amazon Linux, but you can also run a parallel cluster on CentOS 6 or 7 or Ubuntu. Okay, so you can edit the configuration file, change the instance type, change the scaling behavior, and then you're ready to deploy. So these are the commands that we are going to use to deploy. The parallel cluster create cluster name. In my case, I will use the C5 name because I'm running on C5, but you can use any name you want. And then when the deploy is done, you can connect to it using the parallel cluster SSH cluster name command. It's also important to remember that parallel cluster will mount an EBS volume as an NFS file system, as is configured in the EBS section of the configuration file. In my example, I have not configured it, so it will default to the / shared directory. Okay, so let's see how we can finalize the configuration and deploy your first HPC cluster. Okay, here we go. So let's edit the configuration file. This is the file that's been created automatically during the previous step. So what I'm going to do now is I will basically cut and paste the section that we have seen before in my slide deck. Okay, here we go. So we already ran through it. My compute instance type is C5 18x large. The master will be the M5x large, and the base OS will be CentOS 7. Okay, now let's also specify the scaling. I want my instances to scale as fast as possible. So the scale down is set to 1. Okay, we are ready to run now. So the next step is to run the create command. So parallel cluster create C5. C5 will be my cluster name. So basically, it will default, the parallel cluster will default a /parallelcluster config file. But if you have another file, you can specify a different configuration file. Here we go. You see, just after I run the command, a new CloudFormation stack appears in my console, and here you can track the creation of the stack. So the stack is in progress, but you can also control it from the command line. So here you will see every step. It will take a few minutes to complete. Here we go. Okay. Okay, so we have run the create command. Let's see now if it is ready to run. So we can control the status of the C5 cluster. Okay, it's completed. So you can see the status, you can see the IP address, and now I can connect using the SSH command. Here we go. So basically now I'm moving from the administrator view to the user view. So as a user, I can just connect to parallel cluster and run the standard SUNGRID engine command. For example, qhost will give me the number of computing node that I have. In this case, at the moment, I don't have any computing nodes. While the qstat command will give me the number of jobs that I'm running. At the moment, I don't have any job. So this is perfectly reflect my parallel cluster configuration. If you remember, I've asked parallel cluster to start with 0 computing node. And this is perfect. This is basically what I need, what I've asked for. Okay, so this is done. Now let's come back to the slide deck and let's create our first MPI job. So what we'll do to run a very simple example, we'll create an hello-world.sh file, and this will run the hostname command using the MPI run command. So basically, I will run the hostname command on 144 ranks or cores in this case. I will use OpenMPI. This is installed automatically by Parallel Cluster. Obviously, if you want, you can install other MPI flavor. You can install Intel MPI or whatever you want. So I will ask for 144 cores, but this is obviously a number that you can configure. Then we will submit a job using once again the standard SUNGRID engine command, that is qsub, and finally we will see the results in the output file. So, but before we run it, let me also explain to you how it works, what will happen behind the scene. So as you have seen before, user can create a cluster. You launch your cluster. When the cluster is running, what Parallel Cluster will do for you, it will deploy automatically 3 processes. These 3 processes are the core of Parallel Cluster: SQS Watcher, Job Watcher, and Node Watcher. Then user will submit a jobs. Jobs are processed. When the job is done, you can delete the cluster, and the CloudFormation will delete the stack for you. So the cluster is terminated. So now let's dive deeper into these 3 processes, because these are really the heart of Parallel Cluster. The Job Watcher is a process that is owned by root, and it will run, it's deployed automatically, and it will run on the master node. And each minute, Job Watcher evaluate the queue in order to decide when to scale up. So, and it will do it automatically, no matter what type of job scheduler you will use, SangGrid Engine, Slurm, etc. While the SQS Watcher, this process monitor the SPS messages emitted by the autoscaling group that notifies of a state change within the cluster. For example, when an instance comes online, it will submit an instance ready message. And these are used to notify the queue manager when the new instance comes offline or is terminated. So the job scheduler can add or remove the computing nodes to the queue accordingly to these messages. And finally, we have the node watcher. The node watcher runs on each computing node, and basically it controls if there is a job running on that node. And if there are no jobs running, after the user-defined scale-down idle time period, it will automatically terminate the instance. So with just these three processes, we control the behavior of parallel cluster. Okay, now let's have a look. Let's start our first job. Okay, here you see, the shared file system. As you can see, it's mounted on the master node. Now let's create our first job. So via hello-world.sh, let me just cut and paste what you have seen before, the npr run example. And then of course, we need to modify the permission, and then we can run the qsub hello-world.sh command. Okay, it will tell you that EC2 user is not able to run the job, but this is just because I've not added the EC2 user to the job queue. But anyway, the job is submitted, as you can see in the qstat command. So we have one job now in the queue. Is the QW state means that it's waiting, because as you can see in the queue host, as you can see in the output of the qhost command, at the moment there are no node running, no computing nodes. But as I said before, this will trigger the parallel cluster agents, and this will automatically start the qhost command. Let's have a look what's happening behind the scene. As you can see in my console, I have now 2 compute nodes that are being deployed automatically by AWS, and here we go, and by parallel cluster, sorry. And if I look at the qhost command now, I have 2 computing nodes in my SangGrid Engine cluster. So why 2 nodes? If you remember, in my example, I have requested 144 cores. So, and I have selected in my configuration file the C518 X-large instance type. So each C518 instance X-large instances is running on 72 vCPU. And so if I request 144, that means I need 2 instances in order to run my job. And that's the reason why. So parallel cluster automatically detect the right number of instances, and it will deploy it for you. So now we have these 2 instances. And if we can go back to qstat, the job will start running in a minute. Oh, it's already done. Fantastic. So the job is done. Now parallel cluster will shut down the instances for me, and we can control the output of the job. The output has been saved in the hello-world.sh.01 file. Here we go. So this file is basically composed of 144 lines, and the first 72 are for the first 72 vCPU. So you can read the host name of the first of the first computing nodes, while the second part of the file, the remaining 72 lines, contains the host name of the second computing node that I have run. Okay, very good. Okay, now let's see where we can go next. So as I said before, we can use AWS Parallel Cluster to run on the most famous, let's say, the most used job scheduler, but you can also use Parallel Cluster to run, to submit an AWS Batch job. So basically, Parallel Cluster will give you a command line to submit an AWS Batch job. And so now what we are going to do, we will submit one of these example. So the pattern is exactly the same. We have to prepare a new configuration file. We will deploy a new cluster. So in this case, obviously, we will specify a different scheduler. In this case, it's the AWS Batch scheduler. And we have also to specify the VPC, the master subnet node, and so on. It's very important to remember that recently there has been an important upgrade on Batch. Now Batch can also support MNP, that stands for multi-node parallel jobs. So you can now run also MPI jobs on AWS. But in order to use this functionality, it's important to deploy a NAT gateway in the subnet that you will use for your computing nodes. So okay, so that's all. Let's run an AWS Batch job on AWS. So let's come back here. Okay, fantastic. So let's start editing a new configuration file. I will just cut and paste what you have seen before. This is my configuration file. Okay, very good. So now I'm going to edit it. Let's change the region. I want to run it once again in Ireland, West 1. I need to specify my key and also the VPC, the master subnet, and the compute subnet. So for this example, I will use the same subnet both for the master and the compute node. But please remember that if you want to run MNP, so if you want to run MPI jobs on Batch, you need also to deploy a NAT gateway. Okay, here we go, fantastic. So the configuration file is ready. Now I can deploy it. Now you should be familiar with these commands. So it's parallel cluster create. Then I can specify the configuration file with the C flag. And I will also specify the type of scheduler I want to run. And obviously the name of my cluster. Okay, fantastic. So basically now we have two clusters. One is the C5 cluster running on EC2 on C5 18x large, and the other one is an AWS Batch cluster. So we can control, the commands are exactly the same. So if I want to connect, I can use the SSH command. I just need to specify a different cluster name. There we go. So let me accept the K fingerprint. Fantastic. So now I can use I can use the AWS Batch command line to control, for example, the queues. As you can see, there is a queue that has been automatically configured for me. You can check the host that are running. So I have an M4 large instances, and then you can you can use basically all the commands to submit a job and to control the status of the scheduler. So now let's create a first example. So we can create an hello job example, and this is a very simple one, but it's just to give a try. Obviously, in your case, you can then customize it according to your needs. So I have my script ready. Then I can submit the job using the AWS sub command. You have to specify obviously the script that you want to run, and also the parameters for the script. Oh, is AWS B sub. There we go. So the job has been submitted, and ParallelCluster will give you the output of the ID of the job, so you can control the status of the job. At the moment is starting. I can dive deeper and collect all the information regarding the job, like the command that has been run, the log stream, the S3 folder URL, and so on. So now if we wait 1 second, the job will move from starting to running. The job is running. Very good. And in a minute, the job will be done. Okay. Perfect. The job has been completed. So now I can use the AWS bout command to check the output of the job. There we go. This is the output of my job. The job has also saved the output in the shared directory in the secret message for parameter file. There we go. Hello, Franz from computing node hostname. Okay, very good. So we have just seen how to run an AWS batch job using ParallelCluster. Now let's have a look at some more advanced configuration that you can use. So basically, these are more parameters that you can specify in your configuration file. For example, you can request spot. So you can request to run your cluster using spot instances. You can specify a spot price. This will be basically the maximum amount of money you will pay for every instance for every hour. You can also not specify it, and it will default to the on-demand price. It's also very important to have the possibility to specify a pre-installation script. So basically, this is a script that will be executed every time you deploy a computing node. So here you have to specify an URL, an HTTP link, or an S3 link of a script that will be executed every time. This is very useful if you want, for example, to disable the hyper trading. So on our website, you will find some example of script that can, that if you run it before, just after the deployment, basically this will disable the hyper trading for you. Then you can specify the scheduler, you can specify the operating system as we have seen before, and you can also use FSX. So FSX, as you know, FSX for Lastre is our managed version of Lastre. So if you want, you can use FSX, and you can specify all the FSX parameter in the ParallelCluster configuration file. And it will do everything for you. It will deploy ParallelCluster, it will mount in the shared div that you have selected, and so on. So this is very convenient if you want to have, for example, a scratch area for a very IO intensive type of job. And you can also use EFS. EFS is our managed NFS as a service. So once again, you can connect to an existing EFS just by specifying the ID, or you can request it and ParallelCluster will deploy it for you. So EFS is useful if, for example, if you want to. It's useful because it is persistent. So you can, for example, you can save your home directories, or you can run your job using FSX as a scratch area and then save the output on S3 or on EFS. And then you can even destroy the cluster because the data will be saved persistently on EFS or on S3. So thank you very much. Let's summarize what we have done today. We have installed the AWS ParallelCluster command line. We have configured the HPC cluster. We have submitted our first SunGrid engine job on AWS. And finally, we have also submitted an AWS Batch job using the ParallelCluster command line. I hope that this has been useful for you. This is just obviously a first step, but starting from this point, you can easily customize what you have seen in order to achieve your goals. I just want to invite you to ISC. ISC is International Supercomputing, is the most important supercomputing conference in Europe. It will be in Frankfurt Messe from June 17 to 19, and we will be there. We will be at the booth GA20. So if you're interested, please come, because this is a very interesting opportunity to talk with us, to talk to the AWS HPC expert. We will host a number of demo at our booth. So if you want, you can come and we can dive deeper to some of the technology that you have seen today. So I have also added to this slide deck that will be shared after this presentation some links that can be useful for you, documents, other webinars, and also all the links to the technology that we have seen today: ParallelCluster, Batch, EFA, and FSX for Lustre. So once again, thank you very much for your time. I hope that this has been useful for you. And now I'm ready to answer your question.